All right, hello, welcome to Physical Geography, and today we're talking Chapter 5. We're talking about storms. So now that we've kind of gone through the atmosphere, what it's made of, how it works, how matter like water reacts to things like humidity and heat, now we can put all that together. Those are the building blocks, and we can talk about storms and El Nino and climate systems. But let's start with kind of a human example, the tornado. Um, So if we were in class, I would ask if anyone's ever been in a tornado. I have never personally been in a tornado, but I have seen the effects, um, and many of us have. The most intense storm on the planet is what they call an E5, and an E5 tornado, it's a rating we'll talk about, means the winds are over 200 miles an hour. There's really not much that we can build as humans that can withstand that kind of strength. 200 miles an hour winds will pick up a large truck and move it like 50, 60 feet like a toy. And you can see this is the town in Oklahoma, the devastation. Houses just wiped off the ground and left. One of the things we'll talk about, though, was kind of things that we're still studying with tornadoes is sometimes the damage can be very localized. Look at this neighborhood before and after. And you can see right here the definite path of a tornado. These houses are level. These houses are still standing. And that's a space of, 50 feet. So tornadoes come in all shapes and sizes, and we're going to talk about the things that cause those. But part of the first cause, and let's get right into it, are thunderstorms. And so, like all storms and most all weather, we get their energy from the heat, right? The sun heats the Earth's surface, which then also puts water vapor in the air. And it's that condensation of water vapor, that energy that is created or lost when condensation and evaporation occur, right? So, one thing that we'll find with these storms, there's a relationship between the size of the storm and the time they persist. So we call micro scale systems things that only last a couple hours, a brief shower, a small windstorm, right? Whereas synoptic and global events can last months or even years. And so here's an example. When it comes to time, a synoptic scale, these are things that last hours or days, like small thunderstorms. As they get larger, they can last for days and weeks. Hurricanes can last up to a month, and El Nino can last for a year. So you'll notice that as the scale of time gets longer, the size is bigger. A single cell thunderstorm happens right in your neighborhood. A hurricane can cover thousands of miles. El Nino covers the globe. So the larger it is an area, the longer it takes. That's the relationship. So thunderstorms. Here's the shocker. A thunderstorm produces lightning and thunder. So that's the difference between rain and a thunderstorm. If it makes lightning, then it makes thunder. And in the United States, Florida has the most because of the combination of air over the water in the Gulf of Mexico, which is warm and moist, and then cooler, drier air from the land coming down. But when we look at the pattern around the globe, most thunderstorms happen in the tropics over land, not as much over the water, mainly over the land. And that's because over the water, the air is relatively moist. You need that kind of combination of warm, moist air and cool, dry air, which we'll talk about. And how do we measure them, by the way? We can measure from space lightning strikes. So if there's lightning, that means it's a thunderstorm. So this is actually measuring the amount of lightning flashes we see a year. The greatest amount of storms right here in Central Africa, Indonesia, right here, tropical rainforests. If we look at the United States, right, these are the average number of days of the thunderstorm. The greatest concentration is right here in Florida. There's a smaller concentration right here. This is the Rocky Mountains. Remember orthographic lifting? If there's any warm, moist air here that gets blown up the front of the Rockies right here and gets lifted, that causes it as well. The driest air, Pacific Northwest and Alaska, for a couple of reasons. One, the air here is a little bit drier because the Pacific Ocean is much cooler than the Atlantic Ocean. So there's less warm water, which means less moisture in the air. Okay. Another thing to understand is that there are different types of air masses. So basically, air masses are either continental or maritime. So continental air masses are those over land, maritime over water. So think about that. What would be the big difference between land air masses over land and water? I'm going to pause while you think and ponder this. But the difference is air over land is generally drier than air over water. There's just If it's over water, it's got that source of moisture. The next thing we talk about with that is if it's tropical or polar. So tropical just means that it's warm, polar means that it's cold. So combine them. A continental Arctic, this is dry, cold air. It forms over areas like the Siberia, northern Canada, right? You could have continental polar, which is a little bit not quite as cold as Arctic, right? You could have maritime polar, which forms in the North Atlantic or the South Pacific Ocean, right? So cold, moist air. All these different things. Where we see, by the way, the most storms are where these air masses butt up against each other, especially if one has different humidity levels. All right, so thunderstorms. We have three main types: single, multi, supercell. Single cell is kind of the smallest unit, and supercell are the really damaging ones that are huge and have a lot of, sometimes even have tornadoes. So what determines this? Two things. How much humidity is in the air? Think of humidity as gas for a thunderstorm. The more humidity, the more fuel. And then secondly, wind shear. And what that means is, what is the wind doing high up in the air versus the surface? Is there a difference? Are they flowing in opposite directions or different speeds? If they flow exactly the same, if the wind speed at the ground is 20 miles an hour out of the east, and you go up 10,000 feet and it's 20 miles out of the east, there's no wind shear. But if at ground the wind is coming 20 miles an hour out of the east, and at 10,000 feet it's coming 30 miles an hour out of the west, that's wind shear. So let's start with the first one, single cells. Again, these are the very brief ones. Usually you have very little wind shear and they develop in the afternoon. And it happens within the space of an hour. Pretty predictable pattern. Here's what happens. It's in the summer. You have a warm, hot day. The sun is heating the ground. So the ground heats up and the air gets warm and it rises. And if it's during the summer and there's moisture, that moisture rises with it. But like we talked about, right, as air rises, it cools. And so what happens is at a certain point, when it gets up here, the water in the air gets so cold that the water condensates out or turns back into liquid and begins to become rain or snow, right? Now, in the wintertime, if this happens, and it's 0 here, well, then that wouldn't happen. It'd just be snow. But in the summer, anything that falls is going to be rain. What makes it a thunderstorm is that if it's strong enough, right, and it gets really large, and this is when you happen in the summer, you see the clouds just kind of growing. You get all this warm air lifting. There's so much energy that lifts this so far up that by the time that energy that lifts it dissipates and it turns into cold water, it has a long way to go down, and it just comes straight down. And so you get these thunderstorms. And what happens is this process right here, all this warm, moist air eventually gets turned back into moisture, and it basically drains the cloud. So the cloud grows and grows and grows, and then when it rains, it just kind of rains itself out. It turns all the moisture back into water, and when it's done, the cloud's gone. And so these storms basically brew up in the course of an hour, usually in the afternoon. Why the afternoon? Because they've had the whole day of sunlight to heat up. Okay. From that, we move on to the multicell. Now here, the same process happens, but now we add wind shear. And so that means that wind up above is moving at a different speed or different temperature than the surface. And here, we see fronts rather than masses. And what this means is within an air mass, we have two different bodies of air, one warmer and one cooler. Okay? And then as that happens, you get these clusters. Instead of an individual thunderstorm like a single cell, you get rows of them. And if you look at them on a map, you can actually see them like a line of thunderstorms. They call that a squall line. So let's take a look at the imagery. And this right here, you can't see, it's a satellite image, but if that row of clouds, that's the squall line. And what happens is, right here, you have this right here is air that is warmer than air over here. So the air here is warmer and more humid. And so during the course of the day, just like as in the before, that warm, moist air is rising and bringing moisture up into the atmosphere. But what's happening is, now you have wind shear. And wind shear is pushing this whole body of air this way. And this is cooler air. And what happens is, as this cool air hits the warm air, it makes the warm air kind of right up on top of it, like that. And again, same thing. Now the air down here, it finally loses its energy, it turns into rain, and it blows down here. Now, the difference between this and a single cell is this doesn't dissipate as much, because a single cell just stays in place. It grows, and then rains itself out. This is moving, and so it's continually moving into warmer air. See this direction right here? So it's continually moving into warm air. So it's basically running into more warm, moist air, which it converts into cool air and rain. So it doesn't lose its fuel in a sense. And these can last for days. If you look at it from the top, here's the cool air, here's the warm air. It's moving this way. Okay. And the heaviest rain is right here, right where it starts. So right here is the heaviest rain, and then it gradually fades away. All right. Before we get into the next one, I'm going to pause because I need a cup of coffee, and I need you guys to all digest what I said. So we'll start with part 2, multicell, in just a moment.